Hello, RubyKaigi. Thanks for virtually having me. My name is Emily Samp, and I'm a senior developer at Shopify, where I work on the Ruby Developer Experience team. You can find all my relevant internet links, including the slides for this talk, on my website, emilysamp.dev. Today, I'm going to talk to you about some work my team and I did last year, which is generating RBIs for dynamic mixins with Sorbet and Tapioca. Now, that's a lot of words, and they might not all be familiar to you. And if so, that's okay. I'm going to break this story down from the very beginning, and by the end of this talk, we'll have learned the following things. First, we'll set the stage by learning about Sorbet and RBI files. Then we'll talk about the Tapioca gem, first digging into what it is, and then how it works. Next, we'll dive into how my teammates and I implemented RBI generation for dynamic mixins in Tapioca, and the challenges we encountered along the way. Finally, we're going to take a step back and talk about how this work is actually important to the Ruby language as a whole. Let's start from the very beginning by talking about Sorbet. Sorbet is a gradual type checker for Ruby. It was developed at Stripe, and we've been using it at Shopify since 2019. Now, if you're like me, you love Ruby. You love how flexible and expressive it is, how it allows or even encourages developers to harness the power of metaprogramming and duck typing. However, this flexibility comes at a cost. Once most applications grow to a certain size, it can become harder to reason about code at a glance. We can find ourselves spending time figuring out what arguments to pass to a method or what a method will return rather than solving problems for our users. This is where Sorbet comes in. Sorbet can type check our code bases, both statically and at runtime, giving us insights about our code that reduce cognitive overhead and allow us to focus on the work that really matters. In order to understand what's going on in our code bases, Sorbet uses a few different tools. With static analysis, Sorbet can parse and examine our code base to make inferences about our code without us having to give any additional information. For things that it cannot determine from static analysis alone, Sorbet relies on us, the developers, to provide type annotations. For example, when using Sorbet, we have to write out type signatures for our methods stating what kind of arguments they take and what objects they'll return. Sorbet can then use that information as part of its static analysis to type check our code more accurately. And finally, there is some information that Sorbet cannot understand from the first two tools alone, which brings us to Ruby interface, or RBI files. The main purpose of RBI files is to give Sorbet information it cannot access statically or through type annotations written by developers. One example of this is the code inside of gems. Let's say I'm developing a gem called catsay. It's similar to cowsay, where it prints out an ASCII art character of a cat saying whatever message you pass to it. As we can all agree, this is a very important development in the Ruby language. Now, the code for the catsay gem might look something like this. We define a module called catsay, which implements a method also called catsay that takes a message as a string. We then use a docstring to print out that message, as well as the ASCII art of a cat, which is defined in a different method. Now, let's say we wanted to use the catsay gem in a project with Sorbet. We can't just use the gem code in our application without Sorbet throwing a type checking error, because it can't access the gem's code statically. So what we have to do is go to the sorbet/RBI/gems folder and create a new RBI file for our catsay gem. Inside, the RBI is just going to be typical Ruby syntax, and we're going to explicitly write out the module and method definitions from our gem so that Sorbet knows about them. RBI files don't just appear out of the ether. They have to be created. And I don't know about you, but to me, manually writing an RBI file for every gem in my Rails application does not sound like a fun time. This is where Tapioca comes in. Tapioca is a gem that generates RBI for use with Sorbet. It was developed at Shopify, and in 2022, it became the official companion gem to Sorbet, with the goal of making it easier for Ruby developers to adopt and maintain Sorbet in their applications. Now, Tapioca generates RBIs for gems in a few cool ways. It can pull pre-written RBI files from other repositories, and it even provides a framework for developers to write RBI generators for DSLs. However, during this talk, we're going to focus on just one of Tapioca's features. We're going to talk about using Tapioca to dynamically generate RBI files for gems. Before we move on, let's recap what we've learned so far. First, we learned that Sorbet is a gradual type checker for Ruby. Among other tools, it uses RBI files to gain information about parts of our code that it cannot statically analyze, such as code inside of gems. Tapioca is a companion gem to Sorbet that dynamically generates RBI files for gems in our projects. So now that we have that important information under our belts, we can start to understand how Tapioca works on a technical level. In this next section, we'll go through how Tapioca generates gem RBIs. In order to generate an RBI for a gem, we use Tapioca's gem command on the command line. This command will give us some output telling us it's required all the gems in the project in order to compile them. Compiling is the word that Tapioca uses to mean generating RBIs. After some more information, it'll finally tell us that it's compiled the RBI for the catSay gem and created a new RBI file. This is going to generate the RBI file we saw earlier in the talk, which will contain the catSay module and a method definition for the catSay method. But how can Tapioca generate this file automatically? Let's take a deeper look at the process and try to understand what Tapioca is actually doing during gem RBI generation. In the Tapioca codebase, the process of generating RBI is called the pipeline. This pipeline is made up of a few parts. First up is the queue. The queue will contain parts of the gem's code that need to be processed into RBI, and we'll talk more about what that means in a second. Items on the queue will be processed on a first-in, first-out basis by the pipeline. The pipeline is responsible for incrementally generating the RBI file and adding new items to the queue. Finally, Tapioca will create an internal representation of the RBI file for the gem. This is where the RBI code will be kept in memory until Tapioca is ready to write the file to disk. So let's examine these components one by one and really understand how they work. First up is the queue. Earlier, I said that items in the queue are going to represent parts of the gem's code. Broadly speaking, these items are going to correspond to constants, that is, Ruby classes and modules defined in the gem. In our catSay example, we only have one constant so far, which is just the catSay module, but in most gems, there's going to be more than one, so I've added some other blocks to the slide for the purpose of demonstration. In order to populate the queue, Tapioca actually uses Sorbet under the hood. As we've already talked about, Sorbet is capable of statically analyzing a Ruby codebase and providing information about it. By running Sorbet on the gem's codebase and passing the symbol table JSON argument, Tapioca can acquire a list of all of the constants statically defined in the gem's code in the format of a JSON object. Tapioca can then parse that JSON object, identify all the constants, and add them to the queue. Before we move on, I want to be transparent that the process I described is an oversimplification. There's actually more to this process than I'm talking about right now. But because that's not the main purpose of this talk, I'm going to leave it at this level. And if you ever want to talk more about it, please reach out on any of the social media links on my website. So now that the queue is populated with constants, we can take a look at how those constants are processed in the pipeline and used to build the RBI file. The pipeline is actually composed of a series of smaller components called listeners. Each listener has a specific responsibility when it comes to generating RBI to write to the RBI file. For example, there's one listener called the method listener. This listener will find all methods defined on the constant and then generate corresponding code to write to the RBI file to tell Sorbet about those methods. Each listener takes a turn processing the constant. Not all constants will be relevant to all listeners, in which case nothing happens, and the constant is passed along to the next listener until it reaches the end of the list. The whole process repeats itself until the queue runs out of constants. At this point, the RBI file is considered complete and written to disk. Now, this may seem straightforward, but as you can imagine, I've abstracted away some of the complexity of the system. So now that we understand how Tapioca's gem RBI generation pipeline works, let's learn about some of the things that can make this process complicated. Let's revisit the queue. Earlier, I said that the queue will be populated with constants from the gem. However, I neglected to mention a really important point, which is that not all constants used inside a gem are going to have been originally defined in that gem. In fact, I would say most gems have dependencies in the form of other gems. Let's go back to my cat-say gem example. Let's say that while developing the gem, I discover another gem called ASCII art, whose sole job is to create ASCII art strings. I require that gem inside of my own, and then use a method from a module defined inside the ASCII art gem. The next time Tapioca uses Sorbet to discover all of the constants in the gem and populate the queue, it's going to discover the ASCII art constant and add it to the queue, along with the constants that are defined in my gem. If we try to process this constant through the pipeline in the same way that we process the others, this could cause problems in our resulting RBI file. If we take a look at the RBI file for the cat-say gem, not only would it contain information about the cat-say module and the code inside of it, but it would also contain information about the ASCII art module. On its own, this isn't harmful, but it's important to remember that Tapioca will generate a separate RBI file for the ASCII art gem. If we open that file instead, it will also have information about the ASCII art module. Having two sources of truth for the ASCII art RBI could cause sorbet errors and a lot of confusion for developers. So to get around this, Tapioca implements a check in the RBI generation pipeline. Before any of the constants in the queue is passed through the pipeline, they're checked to see if they're defined in the gem that's currently being processed. Tapioca does this using the const source location method defined on object. Taking the stringified name of the constant being processed, this method will return the file name and line number where the constant was originally defined. Tapioca then uses this information to determine if the path is located within the gem that the pipeline is currently processing. If the constant is defined in the gem being processed, Tapioca will send it through the pipeline. If not, the constant is discarded. To summarize what we just learned, we took a deep dive into how Tapioca generates gem RBIs by passing the gem's constants through a pipeline so that they can be processed by listeners who are responsible for incrementally generating the RBI. We also talked about how the pipeline discards constants that were not originally defined in the gem being processed. Now, we are finally set up to explore the main topic of this talk, which is generating RBIs for dynamic mixins. When I joined Shopify in spring of 2022, this was one of the few cases that Tapioca couldn't quite handle yet. I'll show you what I mean. Let's revisit my cat-say gem once again. I've recently decided that it isn't enough for my cat-say method to be encapsulated inside the cat-say module. I want my method to be exposed at the Ruby root level. To accomplish this, I decide to include my cat-say module on Ruby's object class. This is an example of what I'm calling a dynamic mixin. For the rest of this talk, I'll use the phrase dynamic mixin to talk about any calls to the prepend, include, or extend methods that occur outside of a class or module definition, as I just showed in the cat-say gem on the previous slide. Because I included the cat-say module on Ruby's object class, my gem now has the power to call the cat-say method from root. This allows users of the gem to print adorable cats wherever their hearts desire. However, using the dynamic mixin will present a problem in any project that uses Sorbet. If we go back to the RBI file for the cat-say gem, we'll see that it won't contain any information about the object class. The object class was not defined within the cat-say gem, which means that the Tapioca pipeline will discard the object constant before any RBI can be generated for it. This becomes a problem if we try to use the cat-say gem in our application. Let's say we want to write a method in our application called greetAsCat. It prints a cat saying hello world. If we try to call the cat-say method on the root scope, Sorbet is going to complain saying, method cat-say does not exist on my class. This was a case where Tapioca could cause Sorbet to create a type checking error on a perfectly valid piece of code, and we needed to come up with a way to fix it. So the last time we talked about the Tapioca gem RBI generation pipeline, we mentioned that there is a step that checks whether each constant was originally defined in the gem. Well, My team and I thought, what if we could do something similar for mixins? What if we could figure out whether a dynamic mixin occurred in the gem that's currently being processed? If so, we can generate RBI for it, even if it involves a constant that was not originally defined in the gem itself. Of course, Ruby doesn't have a convenient method that would allow us to access this information. So in order to implement a check like this, we'll need to start tracking some information about dynamic mixins in our gem. For every mixin, we'll need to know what constant is receiving the mixin, as well as which constant is being mixed in. We'll need to know what kind of mixin is being performed, whether it's a prepend, include, or extend, and then finally, the location of the mixin. It's also important to remember that because mixins are dynamic, statically analyzing the code base is not going to be enough to collect this information. We need to actually load the gem to collect this information at runtime. So, how do we accomplish this? To do this, we introduced a new singleton object in Tapioca called the mixin tracker. The mixin tracker keeps a reference to a hash called mixins to constants. This is the hash that will store all the information we just talked about. The hash is populated by a method called register, which takes as arguments 3 of the items we mentioned on the previous slide: the constant receiving the mixin, the constant being mixed in, and the type of mixin. In the method body, we find the mixin location, and we'll come back to how we do that in just a moment, and then we use this information to populate the mixins to constants hash. So in order to populate the hash with information, Tapioca actually uses a dynamic mixin of its own. Further down the file in the mixin tracker, Tapioca reopens the module class and prepends an anonymous module to it. Inside of this anonymous module, it implements an override for a few methods. Among them is a method called append features. Inside the method override, Tapioca calls the register method from the mixin tracker, which will populate the mixin tracker with information. To this method, it passes the mixin, self, which is the constant receiving the mixin, and the mixin type, which in this case is an include. It's very possible that you've never heard of the method append features. Before working on this project, I hadn't either. Append features, along with its counterparts, prepend features and extend object, are methods that are deeply internal to Ruby. They implement the underlying logic behind the include, prepend, and extend methods, respectively. These methods are going to run when Tapioca loads the gem. The gem being loaded will trigger all the dynamic mixins that occur in the gem, which will in turn call either include, prepend, or extend, depending on what kind of mixins they are. When these methods call their own internal implementation methods, Tapioca will intercept these calls, adding information to the mixin tracker before allowing the methods to behave as originally implemented. Now, seeing this diagram, you may be wondering, why wouldn't we just have overridden the include, prepend, and extend methods themselves? The answer stems from the fact that overriding these methods is actually a fairly common pattern, and this poses a big issue for Tapioca. Let's imagine that we decided to override the include, prepend, and extend methods in Tapioca. Now, imagine that a developer is using Tapioca along with some other gem that performs the same overrides. Depending on the load order of the gems, it may be the case that the other gem gets placed earlier in the ancestor chain than Tapioca, and its methods get called first. Now, imagine that the developers of the other gem forgot to call super in their override implementation. This means that Tapioca's override will never be called, and information about dynamic mixins will never be added to the mixin tracker. Tapioca's method override will be skipped entirely, which will result in incorrect RBIs being generated, which can then cause hard-to-debug errors in Sorbet. By overriding more internal methods, we can't guarantee that this will never happen, but we do lessen our chances in multiple ways. First, it's just less likely that other gems override these methods because they're not part of Ruby's public API. And then second, even if other gems override include, prepend, and extend, as long as their implementations ultimately call the internal methods, Tapioca's mixin tracker will still be populated and Tapioca will continue to work. To make this more concrete, let's see how this all plays out when we revisit our example from the Katsay gem. In order to generate RBI, Tapioca would load the catse gem, which would trigger this line, where we call object.include and pass in the catse module as an argument. This call to include will trigger the append features method, which we have overridden in Tapioca. Within the method, we will call Tapioca's register method, and we will pass in the following arguments. First, we pass in the object class as the constant receiving the mixin. Then we pass the catse module as the constant being mixed in. And finally, we specify the mixin type as an include. Once these values get passed into the register method, there is then the question of finding the location of where the mixin took place. At a high level, we can do this using the caller locations method defined on Ruby's kernel module. Caller locations is a method that will generate a backtrace as an array of thread backtrace location objects. This array will give us the path for every piece of code that was run in order to get to the method that performs the dynamic mixin. Let's see what that might look like. You can see here that our backtrace would start with the most recent file that was run, which is Tapioca's mixin tracker, where we've implemented the override of the append features method. From there, it goes back to the previous call, which was in the catse gem, where we called include to mix in the catse module to the object class. This list will continue all the way down the stack trace. Now, once we have this array of locations, we need to figure out which of these represents the true location of the dynamic mixin. One potential approach would be to just check the location of the mixin method call. In this case, the include method is being run from the catse gem, which means we could attribute the dynamic mixin to the catse gem. Unfortunately, it's not always this simple. Let's look at a more complicated example of a dynamic mixin, action controller's helper method pattern. Let's say we were writing a Rails app. Inside of the Rails app, we could create a controller, and in that controller, we could write some sort of useful method. The class action controller base actually comes with a method called helper method. We could use this method to mark methods in our Rails controllers as helpers, which means that they'll be available in the view as well as the controller. Under the hood, helper method actually creates a new module called helper methods under the namespace of the controller in our Rails application. Then, it dynamically includes action controller base helper methods on the new module it just made. Now, technically speaking, this dynamic include happens within the Rails codebase and specifically within the action pack gem. However, the include is modifying code that is within the namespace of our application, not within the namespace of Rails. So using the approach we just discussed to find the location of the dynamic mixin in this case would tell us that the mixin took place inside of the action pack gem, and thus that any RBI for the mixin should be included in the action pack RBI. But this doesn't really make sense because the actual functionality change is in our Rails application, not in action pack. To get around this, we had to think of a new approach. My coworker, Ufuk Kaisarliolu, actually came up with a clever solution for this. If we closely examine the array of locations generated by the caller locations method, we'll see that one of the locations has a tag in brackets that says top required. This marks the location where the other gem, in this case just the Ruby core library, is required into the gem being processed by Tapioca. If we use this location, then we'll know which gem required the other one, and thus which gem is the one actually responsible for the dynamic mixin. This even works in the case of action controller's helper method. In Tapioca, this behavior is encapsulated in a method called resolve lock. This method takes the result of caller locations and finds which of them has the top required tag, and then returns that as the specific mixin location. With the issue of determining mixin location out of the way, our mixin tracker is now complete. The mixin tracker is now capable of taking a constant, searching the mixins to constants table, and returning any other constants that take that first constant as a mixin. In addition, the mixin tracker knows what kind of mixin took place, as well as the location of the mixin. So let's see how this gets used in the Tapioca gem RBI generation pipeline. The first step towards finishing our implementation was to create a new listener called the foreign constants listener. This is the listener that's going to use the mixin tracker to figure out whether we should process a foreign constant, also known as a constant that wasn't originally defined in the gem. Let's take a closer look at how this works. The job of the listener is to take a constant from the pipeline, and then consult the mixin tracker to see if this constant is involved in any dynamic mixins. The mixin tracker will find all dynamic mixins associated with the constant and return them to the listener before allowing the constant to continue on down the pipeline. From there, the listener will check if the mixin occurred within the gem. If so, Tapioca will allow the constant found by the mixin tracker to bypass Tapioca's check. Tapioca will then generate RBI for it, even though it wasn't originally defined within the gem. This will also cause most listeners to skip over the constant entirely, except for one listener called the mixin listener, which will generate RBI for the dynamic mixin that occurs with that constant, and I'll show you what that looks like. Once this process is complete, the Catse RBI will have information about the dynamic mixin that occurs on the object class. This will allow us to call the Catse method from the root scope anywhere in our application without Sorbet throwing type checking errors. This means we've successfully used Tapioca to generate gem RBIs for dynamic mixins. That was a lot of information, so let's review what we just talked about. Tapioca generates RBIs for dynamic mixins by keeping track of where mixins happen in a singleton object called the mixin tracker. The information in the mixin tracker is populated by overriding append features, prepend features, and extend objects to register their information. Once the mixin tracker has information about every mixin, Tapioca uses that information in the pipeline to properly generate RBI for the mixins that occur within the gem. Now, we're almost done with this talk, but before I leave you, I wanted to take a step back and explain why you should consider this work important, even if you personally don't use Sorbet or Tapioca. Ultimately, Tapioca is built on Ruby APIs that help us introspect and understand other Ruby code. None of this work would be possible without Ruby's powerful ability to understand and modify other Ruby code at runtime, and that is really, really cool. Because of this, the work we do on Tapioca is going to help us discover the limits of using Ruby for these purposes. A great example of this is finding the location of a dynamic mixin. As you'll remember, in order to find the correct location for the dynamic mixin, Tapioca currently parses the responses of color locations to find the top required tag within the backtrace. What if there was a method on the thread backtrace location object that let us know whether a certain location represented a require? This would eliminate the need for brittle string parsing and make it easier to understand Ruby code through the call stack. This is ultimately why I find working on Tapioca so rewarding. It helps the entire community discover ways in which we can make Ruby a more powerful language. With this knowledge, we can build better tools that help us understand our code and speed up our workflows, like Sorbet and Tapioca. Before the end of this talk, I have a few things I'd like to mention. First, I would like to thank all my excellent teammates on the Ruby Developer Experience team at Shopify for helping me do my best work every day and giving me feedback on this talk. I would especially like to thank Alexandre Terrassa and Ufu Kazriliolu for their work and mentorship on this project. A few of my teammates are actually giving talks during this conference, and I highly encourage you to check them out if you see them on the schedule. Finally, I would like to mention something that is very near and dear to my heart, which is WNB.RB. I co-founded WNB.RB in 2021, and it is now the largest community of women and non-binary Ruby developers in the world, with almost 1,000 members globally. If you identify as a woman or non-binary person, I encourage you to join us. You can find more information on our website at wnb-rb.dev. Thank you so much for attending my talk today at RubyKaigi. I'll leave you with a summary of what we discussed. Enjoy the rest of the conference, and I hope I get an opportunity to see you in person in the future. Bye-bye.